Okay, so today, let's see, the last session, we talked about angle measure in degrees and then radian measure and what radians are. And then we talked about a more accurate way of measuring an angle, and that was using what are called degrees and fractional parts of degrees, which are called minutes, and then also even more accuracy with what are called seconds of angle. And so that's on the previous class session recording. And so what we're going to do today is we want to go ahead now and start. Oh, we also talked, I believe, in the last session about the area of a sector, like a slice of cake or pie or something, and then how much area would be in that. So today what we want to do is stick with the circular type of shape, and what we want to do is talk about what if something is actually spinning in circular motion, and then what's going on there, and how to understand the mathematics of that. And it's not too tough. It's fairly simple. It's almost actually at a beginning algebra level with a little twist tossed in there. So we want to do that, and that's going to be looking at what the length would be on a circular arc. Like if we rotated, say, through 30 degrees, let me use my arm. If we rotated, say, through 30 degrees with the radius of like my forearm length, how much length would be out here on that circular arc? So that's circular arc length. And then when we put that into motion, then that means this point out here on the end where my marker is actually moving at a certain speed, isn't it? Okay, if I give it a certain rotational speed, then there's a certain speed that that object out on the end of the arc is moving. So what we'll do is look at that, and that's called linear speed, and then the rate of rotation is called the angular speed. So we'll look at that, and then also we'll then go over to another chapter and get an introduction to the trigonometric ratios associated with a right triangle. And then we'll try to close today by solving some right triangle problems where we might know the angles and so forth in the geometry. Okay? So let's start by doing something related to what we covered in the last session. If we have an angle given to us in decimal degrees and we want to convert it into the notation for degrees, minutes, and seconds. So let's take an angle. Somebody want to give me an angle that's, say, bigger than 90 degrees? 240. Okay, let's take 242.3591. Okay? Now, if that's degrees, what's wrong with this? What did I not write properly here? I got to put the little degree symbol there like I emphasized in the last session. Okay? Otherwise, that would be interpreted as radian measure. Radian measure. Okay, so let me just leave it at that for this time. So here's how you do this conversion now. We take 242 degrees. We're going to add to it. We take the decimal portion of this and separate it out. The decimal portion we separate out. And then what we're going to do now is we're going to convert this decimal portion here in degrees. That's a little more than 1/3 of a degree. Right? Which means always use your brain and not just your calculator, okay? This is a little more than 1/3 of a degree. Now you know a degree has how many minutes in it, a whole degree? 60 minutes, right? So this is going to be more than 1/3 of 60, which would be more than 20. Okay, so watch what happens when we actually now do the math. So we have in our brain a feeling for the answer. So we now know, we tag a conversion factor onto just this portion, and we know that there are 60 minutes in 1 degree. And so now our degree units disappear, they reduce out. And if we use our calculator on this, we'll then punch 60 times this decimal portion, and that'll give us a number of minutes. Let me just quickly do that with a calculator. You can leave the camera over there on the screen, it's fine. So we have 0.3591 times 60, and we get 21.565 0.546. So the next step is we have 242 degrees plus 21.546 minutes. Notice that's a little more than 20 minutes. Remember a moment ago, we mentally thought about a little more than a third of a degree. A third of a degree would be 20 minutes, so we're expecting a little more than 20 minutes here, which is what we just got off the calculator. Now, we want more accuracy, so we now take the decimal portion remaining here in the minutes, so we have 242 degrees plus 21 minutes plus 0.546 minutes. Everybody okay with this? It's just arithmetic. And then this is so many minutes. Now, notice this is a little more than half a minute. Now, if you break a minute up into seconds of angle, there are how many seconds in a minute? 60. 60 seconds of angle, 60 seconds of measurement in 1 minute. This is a little more than half a minute, so we should expect a little more than 30 seconds here. So we now multiply this by the fact that there are 60 seconds in 1 minute. And you notice now we're again reducing. The minute units reduce out. And this portion right here leaves us with seconds of measure. Okay, now I'll jump again once to the calculator. I take that 0.546 times 60. And I get 32.76, and I'm going to round that off to 33. Okay? So this, the way you'd write this then, is you'd write this as 242 degrees, 21 minutes, 33 seconds. It's that simple. Now, I want you to know how to do this by hand, like I just did. It's real simple. You just break it out with the decimal portions of the degrees first, and then break out the decimal portions of the minutes second next, and then finally you obtain the final result. Now, the calculator has a built-in feature that'll help you with this. So if we now go to the calculator screen and take our original angle, 242.3591 degrees, all right? And if I then take this and go to angle, now the angle key on a TI-83 or 84 type of calculator is on the applications key if you're shifted. So you go second function, notice the cursor, changes to an arrow pointing up, means I'm shifted. And then I'm going to hit the angle key, which is right, it's where the apps key is, or next to the math key. And then item number 4 right here is, if I notice what this means is, take whatever was on the home screen there and convert it into degree, minutes, seconds notation. So I'm going to pick number 4. And that puts that statement right here. Take this and change it into DMS notation. And I hit enter, and there's our answer. Any questions on that? Very simple. I want you not to rely on the calculator, though. I want you to use your brain and be able to do this stuff on pencil and paper. Okay? A number of you came in. I'm going to go ahead and start on the circular motion type of stuff here right now. But a number of you came in late today. I just want to remind you that we're meeting tomorrow in the math computer lab, room 222 over in the math building upstairs. And we'll take care of talking about the class syllabus and the grading process, and then also get you logged into Math XL, which we're going to use for quizzes and tests and so forth. Okay? Any questions remaining from the homework before I start talking about the circular motion topics that are part of that homework also? Okay, let's go. Here we go. how did I help you understand or learn a formula for the area of a sector the other day? How did I help you figure out the formula for the area of a sector? Remember how we did it? What if you don't remember that formula? How did I start? Do you remember how I started? Yeah.
You said the area of a full circle was pi r squared.
Good. We took the area of a circle was pi r squared. Now I'm going to write that in a less familiar form. R squared theta for a complete circle instead of pi r squared. Okay? Now notice that this measurement for a whole circle involves a complete rotation of 2 pi radians, right? 2 pi radians. And what you observe here in this familiar formula is that this is half of that 2 pi radian measure. Okay? So that means then if I have some sector of a circle that's different than, say, 2 pi, call it theta for that angle measure, then if I took half of that theta times r squared, I should have a formula for this thing. So the area of a sector of a circle is half of r squared theta. Theta over 2 times r squared. It's an easy way for you to remember this formula without you having to look in your notes or a book. Okay. Now, related to that same kind of thinking, taking something familiar to create something new, is let's talk about how long that arc length might be on the edge there. If we had, so we're going to talk about arc length. So if we had a whole circle, we learned something as a kid for the length around the outside that we typically call the circumference. Right? You all remember that formula? Somebody back over there want to help me?
2 pi r?
2 pi r, right? Circumference of a complete circle we know is 2 pi r. Now similar to what I just illustrated up here, why don't I just turn this around a little bit and write it as r times 2 pi. Now what happens if I took a portion of the circle, instead of going for a complete rotation like we have for a complete circle, where we have a complete angle, 2 pi radians, to get completely around for a circumference, and that's the length on the edge out here. That's this length around the edge. Then it looks like if I cut this into a sector, and let's see if I can just squeeze it in here, a sector of a circle of some angle theta, then this arc length right here, let's call it S, this looks like the measure of the angle, doesn't it? Doesn't that look like the measure of the angle right there? Central angle for the amount of rotation from the initial side to get your terminal side lining right up with it. That's 2 pi radians, isn't it? So it looks like the sector of a circle would just be proportional to what you see here. So the formula would be, given r and theta, S, the arc length, would be r times theta. R times theta. Anybody confused by that? Please be honest. Anybody confused? 1 per 2. Anybody else?
I can't really see it.
Oh, that's one. Okay, you're in the back row. Okay, right.
Well, that would help.
Okay, that would help. Okay, now, okay, let's just step through that. I just want to make sure you're really good with that, understanding that. So we know for a complete circle that the entire arc length for a complete circle is your familiar 2 pi r, but I'm going to write it this way. Now what if I took half of a circle, like I did the other day with you? Half of a circle, what would be that arc length?
R 2 pi over 2.
It would be half of this, wouldn't it? And if I did a quarter of a circle, that arc length right there would be half of this one, wouldn't it? So that would become a pi over 2. So all we're doing really is observing a pattern recognition. So if I took some sector that was of central angle theta, instead of pi over 2 on the quarter circle, or pi radians on the half circle, or 2 pi on a whole circle, if I took some sector called theta of central angle, you can just look at this pattern and see that it has r in it, and it has the central angle right there in radian measure. So the arc length is the radius times the central angle. Yes?
I must just not see it, but I don't understand why you rearrange, what the point of rearranging them is. You just like from 2
Okay.
pi r to
Yeah.
whatever.
I'll show you that with an illustration right now. Good question. I want to point out to you that this is an algebraic relationship. It's a linear relationship. It's a linear relationship. What are we holding constant? No matter what size sector we talk about. What are we holding constant here? The radius, aren't we? Aren't we holding the radius constant? So we're dealing with a circle. A circle. We're holding the radius constant. Theta is allowed to vary. The central angle, you can see, is varying in value. Okay? This is no different mathematically than what you're familiar with from beginning algebra. Y equals mx. Where you hold, when you're drawing a line, you hold a certain slope. And you just move, you let x change, and your y values keep changing as you let x change. And the thing that's being constant is the slope. So this is a linear relationship where r is kind of a constant of proportionality, or it's fixed, it's a constant value. Okay, let's do an example, and I think you'll see those who had a question about this, it'll offer some clarity. So let's say somebody gives me an angle in degrees. Somebody give me an angle bigger than 90 degrees.
135 degrees.
135 degrees. So we're going to let theta equal 135 degrees. Somebody give me a radius in the American system of measurement.
8.
8 miles? 8 miles. Okay. Now, that's going to be one big circular arc, isn't it? 8-mile radius, and I'm going to draw a picture. So here's my 8-mile radius. And I'm going to go, Tim suggested 135 degrees. Oh, I like that, Tim, because that's one of our 16 angles we talked about the other day. 135 degrees is 45 degrees less than 180 degrees, right? So it's going to be pointing right back up this way. And same radius, 8. And then we have this circular arc, don't we? Right there. And what we're interested in is the length of that arc. And the central angle right here in the picture is 135 degrees. Okay? So what we do typically in math is we write down what we know, and we have usually some kind of relationship that we're putting this known information into. So the relationship we know is we're interested in finding that arc length, the length of the arc, and our formula is this that we're using, and we put these values in. So we're going to put in our 8 miles right here, and then we're going to put our 135 degrees in right there. And there's something wrong here.
We have to change the radius.
Right on. We have to convert this to radian measure. Look back at what we just talked about here. We don't use 360 degrees here. We don't use 180 degrees here or 90 degrees here. We have to use radian measure for that angle theta. Always. So what we do then is we come into this formula and we write down our given information as we did, and then we're going to have to convert this to radian measure. So we tag on a conversion factor here. The fact that there's pi radians in 180 degrees, that conversion factor is effectively 1 in value. We're multiplying this product, r times theta times 1. And look what happens. What disappears? The degree measure disappears, and we're now left with mile radians. That's strange. Is that length right there mile radians physically? Think about it. If you're out there on eastern Oregon on the flat desert, and you're out there jogging or riding a mountain bike or something on that circular arc, are you traveling mile radians out here?
No.
Heck no. You're traveling a certain distance in miles, aren't you? So something's screwy right here.
Gotta get rid of the radius.
Okay, so here's the way I do this. I never see this in a textbook, but here's the way I get that confusion out of my head. What did I say a radian was in the last class session? What's a radian? How do we find a radian? Don't remember the story about the wet noodle? Ah, you take that piece of string or that piece of spaghetti that's been cooked of a certain radius, certain length, and you bend it on the arc, right? And that creates how much rotation? From the initial side to that terminal side. How much rotation is this? 1 radian. So this radius of length is equivalent to 1 radian of angle measure. Does that make sense? 1 radius bent on a circular arc is equivalent to 1 radian of central angle measure. So this 8 miles could be thought of, this 8 miles right here, could be thought of as equivalent to 1 radian of angle measure here. It'd be about that much. So in the formula here, when you see the radius in this formula, this is really a conversion factor. Miles per 1 radian. On a circular motion. In circular motion, folks, the radius can be thought of as a distance per radian. Stormy?
Oh, maybe. Can you say it one more time? Like, if the radius is 8, how do you know how, just like looking at, how do you know how far over that 8 would go?
Okay, you're going to bend it. You're going to bend this length 8 along this arc, and it's going to come up, wouldn't it come up about that far?
And how do you know that roughly? Like,
Oh, I eyeball it. Doesn't it look like it'd go about that far if I bent that length?
can we look at it and know how many 8s we would have?
No.
Okay.
Well, yeah, there's going to be more than 6 of them to get all the way around.
Okay.
This angle right there, this central angle right to get us right to here is 1 radian of measure.
Oh, yeah, okay, click. Got it.
Good, okay. Sometimes you have to tell the story several times for it to sink in.
Thank you.
The best way for this stuff to sink in, I've said this before, is for you to be talking to each other. Or tutor. Or teach it. Okay, that's the best way for you to get this stuff down, is by verbalizing it. Okay. Everybody with me now? It's a very simple formula, beginning algebra level, y equals mx, but it's very important that you understand that this is the fundamental formula. It comes from our understanding of this. is one easy way to think of it. And then we write down the governing equation, the given information, a picture, and then we drop in the goodies and convert the units if necessary. Now, look at that. That turns out to now be a length in miles, doesn't it? Which it should be, which it should be. So the arc length then is, oh, here's something else. This is, again, 135 degrees that Tim offered is actually, we know, one of our 16 angles. Think about that. We played a game, and I need to start bringing a stick in here so I can, instead of my arms, okay? We went 45 degrees, didn't we, the other day? That's 140, that's pi over 4 radians, isn't it? Quarter of pi? Okay, so that's 1/4 of pi. 2/4 of pi is 90. 3/4 of pi is 135. If you reduce 135 into 180, you're going to get 3/4. So if you knew off the bat that 135 degrees was 3/4 pi radians, you could have just dropped that in right there. You could have done your 8 times your 3/4 pi without having to have made that extra step right in there. And at that point then, what you're going to do is you're going to multiply this out with your calculator, but pause for always think. You'll hear me say that many times. Use your brain first and then punch your calculator. So look up here. If you took this 8 miles and laid it on there, and we're going to go 3/4 of pi to get around here, then another 8 would be about here. You can eyeball it from your sketch. Okay, so there's 16 miles. You better expect an answer probably a little bigger than 16. A little bigger than 16 miles when you punch this up. Then you turn your calculator on and you better get an answer in that ballpark. Okay, back to the calculator. So we're going to take 8 times 3 pi divided by 4. If I could punch this right. 18.85 miles. What would be an exact answer if you clean this up? Look at the arithmetic here.
You reduce.
4
into 8 twice, 6 pi. 6 pi miles. So an exact answer would be 6 pi miles. And an approximate answer is 18.85 miles. You want to be comfortable with both. And notice the difference in the way in my writing. Exactly equals shown here. And then if I'm writing down some approximation off my calculator or some kind of mental estimate, I'm going to use some kind of a curly equals sign to indicate approximately equal. Big distinction between the two. Yeah.
Just to clarify, the conversion that's left over, your pi over 180, that's just 1, essentially.
That's a conversion factor that's equivalent to effectively 1 as a multiplier times this. Mm-hmm. Yeah. And as I mentioned the other day, it's the same as reading a map. You might look on a scaling on a map and it might say 1 inch equals 200 miles or something, right? So 1 inch on your map is equivalent to 200 miles. That's effectively a conversion factor. Okay? Driving your car, riding your motorcycle, 30 miles per gallon. That's a conversion factor. And you could multiply that 30 miles per gallon times a certain number of gallons that you've used, and that converts you into miles traveled. You do that all the time in life. Okay. Okay, very important. Are you ready to start putting this into motion? Okay. We haven't been moving yet, have we? This has been static. Okay. Question? Yeah,
I just had a quick question on the, on your homework on formatting.
yes.
Like on the problems on homework, I didn't put the rad, I just dropped the rad, in the conversion factor automatically.
Yes.
Are you gonna dock for that, or is that?
No, I'm just showing you, I mean, you want to be, keep in your brain what I just did here. That's important, okay? So keep in mind what's going on there, and on your work, you don't necessarily have to write that down.
Okay.
That's fine. Another question?
Are radians always referred to as RAD, or is there a symbol, or is there
There's
something
no
else?
special symbol for it,
There's
but
no
I usually
uniform.
just write RAD down. Mhm. Okay, now let's come back over here to what we're covering today. What we just covered it with an example is circular arc length, segment 1. So we pretty much finished that discussion. So what I now want to do is we'll go ahead and end this segment. You folks ready back there? We'll end this segment and then we'll start talking in the next segment about linear and angular speed. So there's supposed to be some kind of image they're going to kick up over here. There it goes. Okay. Okay.